Bom, primeiro agradeço por a invitação e quero dizer que eu ia falar em portunhol, mas aí eu tenho uma estudante que ainda não é estudante, que está se candidatando, que provavelmente vai ser minha estudante, ayer, e ela me pediu que prefere em inglês do que em portunhol. Então, acabei escrevendo em inglês, ela provavelmente não veio, então não sei o que, vou falar em inglês de qualquer jeito. Então, eu cambiei o título, porque esse título faz mais sentido. O primeiro título que eu mandei era o primeiro título que tínhamos em el trabalho, e é bem, eu creio que é bem interessante usar esse título e não o outro.
Exacto.
Digo em puro portunhol, uma lição de portunhol gratuita, trabalho em conjunto com Código Civis. Em portunhol, o N se escreve com a M e o com também. Tá bom? Okay, now I change to English. The agenda, first I will define what's a k-category and Galois covariance. Then I will define the Hochschild-Mitchell cohomology that mimics the Hochschild homology, and it does mimics the Hochschild homology. Then I will define relations between the Hochschild homology of C and relation of homology of CG. Then I will take the main result, I will talk about the main result, and then the idea of the proof, the definition of this. For the proof, you are going to need the definition of the skew group category, and thus will be defined. And thus is something really surprising. It's completely closes the idea. The auxiliary category MGC, which is resolving. Thus things says more or less that free actions is not a strong hypothesis, because in the proof, we are going to use first that the action is free, but then with this resolving category, we can show that it doesn't matter if it's free or not. We can take we show it for free, and then we do it for the other one. And then one or two words in cohomology if I have time. Okay. K will denote a field or any commutative ring, a k-category, or as a referee of another paper that we had required, a category enriched over a k-modulo category. If you like this more than k-category, you can use that. For me, we are going to use just k-category. What is a k-category? The objects of C form a set, C naught, and the composition is k-bilinear. Mitchell called a k-category a ring with several objects, rings with several objects, because we can think in a ring as a k-category where there is only one object, and the morphisms is the whole any k-algebra. The morphism is whole the k-algebra. So okay. I'm going to give you some constructions that this is a construction. I will not insist too much on this, but in the paper that we read, we make it clear that all the notions that we do really extend the known notions for rings. So that for k-algebra. Suppose that A is a category, and then you take A of C, the direct sum of x from xy of cxy. I think I defined the cxy. No, I don't define. Okay. Those are the morphisms from x to y. We denoted that way. And multiplication is matrix-wise. It's more or less clear how you define. This is a ring which is a k-algebra. No, which is a k-algebra if if the C naught is finite. If C naught is finite, then it's an associative ring with identity. If C naught is not finite, it's also a ring, but then without identity. And it's not a k-algebra in some sense. All results on construction here can be done at the level of algebra. A lot of them is already been done, and I will not translate it. What I mean, a lot of things that constructions that we do for the categories, when C is fine, when the C naught is finite, is already done some places for AC. And I will not state all the time that when we take the ring, this notion is the notion that we define here coincides, restricts to these notions in the rings, in the ring AC. Okay, let me give you one example. This is example which I have always in mind, or some quotients of those examples are the examples that we work all the time. Suppose that Q naught and Q1 is a vertex, is a quiver. Okay, O is the origin map and T is the terminus map. Then we can form a category as follow. The objects are the vertexes of the category, and the morphisms is the vector space which bases the set of paths between V and W. One extra ad hoc path of length 0 for any vertex. You want a category, then we need the identity. Thus, if we don't do this doesn't have an identity. To have the identity, you need to put ad hoc the identity. So you put one vertex. I think people here know that. Okay, and the multiplication, you do the multiplication saying that when you compose one guy two elements on the basis, the composition is 0 if W is different from W prime, is the concatenation or otherwise, or the map induced by concatenations of the paths. Okay. One paper where a lot of this thinking that I'm taking here is my paper is one of the papers that I like most of myself. I mean, everybody has his preferred paper, and my paper, this is probably the preferred one. Does an almost all concepts on the Stoke, the idea that the concepts is described almost all. Is a paper also by Claude and myself that's called Skew-Categories, Galois Covering, Mesh Product, and Group Actions. I think this reference is nice also to look at the references that are there. You can see what was done before and etc. So I really recommend this paper. It's of my papers, one that I like the most, one of them. Okay, let G be a group. So let's do this, is the definition that appear in that paper. Let G, what is a G category? So G is a group. A GK category in C, a JK category C is a K category which has a G action by autoequivalence. That is, there is a group homomorphism G out in the automorphisms of the category. Automorphism is a set of F equivalence. In more details, we have an action, an usual action on the objects. This is an usual action, and if S is in G and XY is in C naught, so the X and Y's are X and Y's are objects, you define a multiplication by X or action by X, CXY in CX SXSY, and the identity of compute, if you have x, the identity go in F to F. This probably is a consequence of the other ones, but doesn't matter. And then if you first act with S and then you act with T, is the same as acting with TF in every F. And also, if you take S and apply in a composition, is the same as applying S in the first one and S in the second one. Okay. When C0 is not, AC is a k-category unit, and what we define here is a usual action. So you have an action. Okay, let me give you one example, also with something. Take G equals Z over 4Z, that's the group, and C equals KQ, where Q is does quiver here. So I have I have 8 vertex that are propositionally numerated by A0, A1, A3, and B0, B1, B3, and I have this is the set of vertex that purposely are numerated by alpha 1, alpha 2, alpha 3, and B0, B1, B2, B3. Okay. If you think, if you forget even, this is a covering of this quiver here. If you think in the topological space, it's clear that this is a covering of this. But now is the cover respects is really the morphism of quivers. G acts here. G acts here. How G acts? Why I did this? What? G acts here in the most natural way. G, I take G as generated by Rho and say how Rho acts. Rho take one vertex to the next one, modulo 4. Okay, in here and here. And arrows also take this arrow to this arrow to this arrow. Okay. And this arrow goes to this one. And this
Pero,
one.
Eduardo, la última no termina en A0 en vez de B0.
Verdade, é verdade. Tá bueno. Tá muito simples. Okay?
Era como raro el dibujo.
Sabia que eu tinha assim, depois quando eu passei a limpo, quando eu passei, eu cometi o erro. A última vai em A0, senão não funciona. Tá bueno. If we suppose that the concatenation of any t arrows to be 0, then that ring that I define AC, if I don't say anything, the ring AC is just KQ. If I assume this, the ring AC is KQ divided by J to the square, by J to the cube. So this is an example. And then we can define in some cases, we can define a quotient category when you have an action. We assume that the action is free on the objects. Free means free on the objects. Then it's obviously it's going to be free on the morphism, because if it's free on the objects, it's free on the morphisms. What free means that if gx equals x for some object x, this implies that G is the identity. In this case, we can define a quotient category as follows. The objects are the orbit sets on the morphisms. And the morphisms between alpha and beta now is an orbit. You take the sum of x, the direct sum of x, y, x of cxy for all xy, for all alpha for all x in alpha and y in beta. So you take the whole sum. This is a G modulo. This is a G modulo. Then you can define the objects are going to be the objects of this is you take this G modulo and and take away you divide by the elements of the form sigma plus G of sigma with G in G and sigma here. So in a sense, is the maximal, you divide, is the maximal quotient where G acts trivially. The composition is done in a very natural way. And if G is finite and G minus 1 is K, then this guy here is equal to this. This is called the coinvariants. It is isomorphic to the invariants. A warning is that Bongartz, Gabriel, Martinez, Villan, De La Pena define the G-Galois covering a bit distinct. They took always the invariants, not the coinvariants. But in general, they cannot get a very similar theorem. One theorem that is very nice in this theory is a theorem of Cohen-Montgomery that's called the duality theorem, and a lot of some other things that using the definition we get this theorem, and using the other definition you don't get. But also, like I said before, sometimes that both definitions are equivalent. And we call this a Galois covering. A Galois covering is anything that is isomorphic to this. So if you have, if you take GC here and you take an isomorphism and you take a map and this isomorphism commutes, we say that this guy is a Galois covering of this ring here. And here you can take isomorphism. So you can define a Galois covering. And there is very nice theory that can be done relating Galois coverings and gradings and so on. Our work was to show some theoretical connections between the Hochschild homology of C and the Hochschild homology of some components of the quotient, and also something from the Hochschild homology. We did this first to define this thing here. We need the free action, but then we generalize our results when you don't have free action necessarily. That was really very nice, I think. We need to define the Hochschild-Mitchell homology for k categories and Hochschild-Mitchell cohomology. And I will define. The Hochschild-Mitchell homology for k category is the following. You have a k category, you define the following complex: C0, C1, C2, Cn, where Cn, you put any terms here, any plus one term here. And observe that this one has to be, the orange of this one, of this set, has to be the terminus of this one. Does Cx0, x1 means the morphisms between x0 and x1. Then the morphism between, here I need the x1 and x1, x2, so that in the definition, I will compose two successive ones. So I need this, and the last one is equal to the observed one. Observe that C0 is just the sum of Cxx. There is no other, that's the C0. And then you define, so you have, here I define Cn, and now I will define what is the differential. The differential is just given by that. You up to here, you compose everything, and then you put one more when you put this x0 to the f0. That's one reason perhaps why we need in the formula at the beginning that this can be composed. Okay. One can show in the usual way that the d square is 0, and the nth cohomology of C is what is not the Hochschild homology of degree n of C is by definition the homology, the nth homology of this complex here. If C is a k-category with a finite number of objects, another time one can show that does coincides with the usual Hochschild homology. Okay. So let me say a theorem is that suppose we have a Galois covering. Then the complex C can be decomposed, the complex can be decomposed in sum of complexes. And what you do is to do the D, you what I said? Okay, you can decompose in complex that they are thus complex here. What happens is that I didn't define what it is, but this category here is graded. Thus there is an action, then thus is graded. There is a way to grade this. And so the complex C for a graded algebra in general, for a G-graded algebra, no, for a G-graded, it doesn't have to be Z-graded. You define the complex that we, what is the complex? The complex. You see the complex here and how it's defined. You can take, okay, grade a category means that you grade the morphism in a compatible way. That's what grading a category means, to grade the morphisms. Okay, so you have Cn here. Every Cn here can be decomposed. You can, those guys you can decompose in degree S1, degree S2, and so on, and do a direct sum. The things of degree D, where D is we decompose in the conjugacy classes. And what happens, the conjugacy classes is the conjugacy class of C0, C, you multiply C0, C1, Cn, 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 C0, and you see what is does in which conjugation classes does is, and because the way is defined here, the conjugation class is respected, so you can take this complex and divided and split it in a direct sum of complexes, each one with respect to the conjugate classes. So you can do that. Okay. And this guy here is a KG model. If this functor is exact, there is an isomer, otherwise it's a little bit different. If this functor is an isomer, is exact, then when you take the coinvariants of this guy here, is the same that take the Hochschild homology in degree 1 that I said here of the quotient. It's the same thing. Usually you put this G out, but then when this is out exact, you can put this G is valid. Okay, then some observation. The first is that this first thing here is valid for any G gradient category, and CG, C over G, the coinvariant category, or the the quotient category is graded. For algebra, this was obtained by M. Lawrence, this thing here. For algebra was obtained by M. Lawrence. So corollary, suppose you have a Galois covering and that this functor is exact. Then there is a monomorphism between this is isomorphic to this. So there is a monomorphism between this invariant here with the Hochschild cohomology of C over G.
Eduardo, what is the symbol on top of the Hochschild homology on the right?
Here is, you see, I said that complex can be decomposed with respect to the conjugate classes. And here is the homology when you take the complex and take the conjugate classes equal 1. See, I said here that this complex that defines the when the algebra is graded, this complex that defines the Hochschild homology, this guy here, can be decomposed in a number of complexes, each one indexes by the conjugate classes. And what I'm taking here, there is the conjugate class of 1. Another way to, what? This gives us a grading in the Hochschild cohomology, and I'm taking the degree 1 also. Yes?
Yes, perfect. Thank you.
Okay. So, but the way we do, in a sense, is that this guy here can, every time you have a grading, this guy can be decomposed, and what I'm taking here is, and the decomposition depends on the conjugation classes, and I'm taking the conjugate class equal to the guy that is respect to the conjugate class is 1. That's one here. But this is a subset with a lot of properties of the whole Hochschild homology. So there is a monomorphism between this and the Hochschild homology of this guy here. This even can be seen in this paper that I took with Ed with Claude, and this kind of solve. I have one paper with Isabel and Martinez Villa, where the result is wrong, but we did a mistake that at that moment I didn't realize, but does kind of fix it. Okay, but this one here is valid for any time you have a G-graded algebra. You have a G-graded algebra, you can do that. By the way, every time you have a G-graded algebra, that's what we showed with one thing that we showed with Claude in that paper, is that it is the quotient of Galois covering of something. So if this is grading, doesn't matter what does happen. So this is valid for any grading, but you can define directly without using coverings, but we can use the. So you have a Galois covering. Any graded category can be put in the setting. You can construct something called the smash category, and there is a Galois covering between the smash category and the category if it's graded. You take the grading and you kind of use the idea of the smash product of rings, and you define the Galois covering here. By the way, we didn't do it, but this probably can be done with this in category with the smash product when you, instead of an action of G, you have an action of a Hopf algebra. We didn't do that anyway, but we could do. I believe that this can be generalized for the setting of Hopf algebra. Okay, now the main ideas of the proof. First, instead of using the CG, we use an equivalent category to it that is CG, the skew group category. What happens is that in this paper of Claude, what we did is the following. You take a graded category, then you take the smash product. Then there is something, every time there is an action here. Every time there is an action, you can define the skew group category. So you take this and you have this skew group category. Our theorem says that this category here is equivalent to the skew group category related with this. This is Cohen and Montgomery have the proof this for rings. They say that if you have rings, if you have a graded ring, you have the smash product, there is an action of G, and you take this skew group ring, and what they show when G is finite is that this skew group ring of this guy here is matrix rings with order of G over the ring. So they are Morita equivalent. That's what they show. And there is other one also. There is another one, but this is one of them. And this is valid in the context of categories. And it's proved in that paper there. Okay, so we have that this category is equivalent to this category. And then we use a result of Herskovich. Aqui é S, não é? Não é Stanislaw, é S. I kind of make it Brazilian because in Brazil there is various Stanislaw, but no one is an S. So Stanislaw Herskovich, he showed, I think, in his work on the undergraduate work under the supervision of Andrea, he showed that if you have equivalent categories, then the Hochschild homology of the equivalent categories and the Hochschild cohomology, they are both equivalent, they are both equal, so it doesn't depend. Okay. By the way, I have a question that probably also Andrea knows the answer, I don't know. Stanislaw showed that when you have two equivalent categories, then the Hochschild-Mitchell homology of one is equal to the Hochschild homology of the other one. Okay. Suppose the category of modulus over this category, thinking modulus as functors from the category to the abelian category, to the category of abelian groups, or if you want K to the K vector space. Suppose that those two categories are derived equivalent. Is true, or it's probably true. I don't know the proof that the Hochschild homology and the Hochschild cohomology, the Hochschild-Mitchell homology and the Hochschild-Mitchell cohomology is also equal.
Eduardo?
Yes.
Sorry, I didn't understand the definition of a module category.
A module over a category is just a covariant, depends if you take modulus on the left. It's a covariant functor from the category to the category of, if you are over K of K vector space. In general, if you have a category, a K category is, you take if any K, you take the modulus You take a functor from the category to the category of the category of k modules, or in general to the abelian group category. Thus, if you think in ring, you can think in a category as one object, and if you think as a category of object, a modulo is just a covariant functor from this category to the category of abelian groups.
Yes. So in case of the example you were saying about a quiver, it will give like a representation of the quiver.
It's a representation of quiver. A representation of a quiver, by the way, can be defined that way. I mean, yes, you take that category and take a modulo. You can define, it's defined even for when k is not finite and etc. It's just that, it's just a representation, yes.
Thank you.
But in general, if you think in a category with one object, is that way. If you take a category with any objects, like that is the same. If you take a finite quiver, for instance, for every element of the quiver, you define one element, and then it has to respect the composition. It's just a functor. By the way, this was very, very successful of Maurice Auslander, my advisor. He always think on models that way. And then for an algebra, he showed that the category of, then he take what modulus is finite generated means that they go to the finite dimension vector space. And he taught in a modulo as a functor, and he proved that the category of functors, over the modulo category has global dimension is smaller or equal than 2. And using this, he showed the existence of almost split sequence that was real something very important in representation theory. And the first way that he showed the existence of almost split sequence was using the functor, thinking a modulo as a category. Thinking in a modulo as a functor from the module to the category. And then he take, this is another category. What is the functors of this category? And then he showed that the functors of this category is an abelian category with global dimension at most 2. And then he was able, because of this, he take the simple functors and etc. This was very successful way of thinking in this way. He was a guy that always taught very functorially. So this was very, it's not just a changing, he really, how Maurice shows, he really sometimes give you some good ideas to define as a functor. Okay. Now we define the skew group category. You have C, a category where G acts. Okay. Then I define as does is defining that paper that I said that is together with Claude. The objects are the same objects of C naught. And the morphisms is the sum from S belonging to G of C, X, S, Y. This is morphism from X, Y. If the composition is some kind of natural, if you want to compose, you have to take the second morphism and make the action. That's why you need the action, because the action is used, that you have an action is used to define the composition here. Okay, then if G acts freely on C naught, then this guy is is equivalent to this category as graded category. Both are graded, and thus is equivalent as graded category. Remark from this one, we obtain the duality on Montgomery. Theorem of Stanislaus. If C and D are equivalent category, then the Hochschild homology of C is the Hochschild homology of D. Question is that we take mod C. Mod C is the category of functors from C to K modulus, and D the same. And suppose they are derived equivalent. Does it follow that those are equal also? Obviously.
But for Morita equivalence, it is in that paper.
Yes.
For
From
derived
Morita
equivalence, I think it is the same because they behave, Hochschild-Mitchell behaves in the same way as Hochschild homology.
Yeah, I think probably should be the same, but the fact that it's not done there, so it's perhaps
Yeah.
but it's true that it's probably the same. For instance, if C has a finite number of objects, then this category is a category of modules, and then this is Morita equivalent to this one, then it's true. But I think the finite number of objects is not necessary. Just something that I think that would be nice to give to an undergraduate student to continue to finish and to see, but no, undergraduate is too much because usual undergraduate student don't see derived equivalence, etc. But even a master's student to start, I think is a nice. I thought yesterday that is a nice project to do. Okay, it showed us also for derived equivalence.
But this was the master thesis.
Claude had told me that was the undergraduate something.
Well, undergraduate, which is kind of equivalent, but you must remember that undergraduate here is 6 years.
So it's like, okay.
Yeah.
Okay, but anyway, then we showed that this guy here is isomorphic to this. The component one is isomorphic to when the action is free. So if the action is free and this is exact, we get this, and this. This goes, each one goes, because this guy here is equivalent to this, and then we have, using this theorem, we have this. Now, can we drop the hypothesis of free action? That was something really, really nice, I think. The idea was obvious clothes. The answer is yes, and justifies the title of the talk. I said the talk is resolving. The idea that is very, very behind is that everybody knows that the K modulo category is equivalent to the MNK modulo category. Okay,
but Eduardo, sorry to interrupt, it is in the paper for the derived equivalent. I was just checking.
Okay, sorry, I thought it was.
Yeah, it's theorem 215. Yeah.
It's doing there for derived, so it's not anymore. So the answer is done. I knew that probably.
Yes.
Also, perhaps we can. Okay, so coming back, this is also true for derived equivalence. So it's true, and it is in the paper. I should have read the paper more carefully. True, and it is in the paper. Okay. Okay, let's see. It's a K category, GK category, with an action, GK category. So we have an action of G, but it doesn't have necessarily to be a free action. Then we define MGC as follows. MGC, the object is G cross C naught. And when you take SG to ST, the morphisms doesn't look to the elements of the group. It's just same as morphisms of the group. Obviously, I should probably put an isomorphism here because the morphisms are different because they have, this guy is not here. It's a copy for each one. And composition is a very, very natural way. It's like matrix. Though the proposition that we have, C and MGC are GK equivalent category. And clearly G acts freely here. The action of G here is just taking SG and you put G here. So G acts freely because this guy doesn't stay the same unless G is equal 1. So now we have a category that had this category that we showed that is equivalent to C and G acts freely. So we take this guy here, this is isomorphic to MGC, and this is, and Gershkovich showed that this is equivalent to this. Because now the action is free, and you can do the computation, you can do the, no, here the action is free, and you can use the former theorem. So you can use the free action to prove the non-free action. One thing that I think perhaps it's nice we are not able to do is suppose that the action is not free to show this theorem directly. At the first version that we had, we assume all over that the action was free. Then one day Claude called me and say, okay, it doesn't matter, we can, every G action is equivalent to a free G action, some sense. Okay. Now, how we do it for Hochschild-Mitchell cohomology. The ideas are analogous. It's a lot more complicated, but it's analogous. The complex C that we had has to be changed by C. C naught will be this, and Cn would be a sum of homomorphisms from here there is a tensor product. We don't repeat the beginning and the end another time, but we repeat x1 and xn here. And you take the homomorphism. Now you have to take the direct product. That's much more complicated to work than with the direct sum. And the composition along the classes D is more complicated. We also use another time Gershkovich for cohomology, and that's how, I'm not going to do it because the idea is more or less the same. I say muito obrigado, gracias, merci beaucoup. Thank you for hearing. Okay, that was more or less what I had to say.
Gracias, Edu. ¿Preguntas?
I was curious in the last part, at the end where you have this big product, which you say it's harder to work with. So at the level of C, you don't have a grading, but you have a G action, right?
Yes.
In
CG, no, C over G, the quotient you have a grading. In the quotient you have a grading.
But here you only have an action. And why is it so much more complicated with the product?
Here, in some sense, you don't have anything. You have just C is a category, and you define the Hochschild cohomology. The objects that appear is a complex where Cn is going to be this. And then if you have, if C is grading, you also can decompose this in a more complicated way, but you can decompose this along classes D. I mean, this definition doesn't depend on action. This is the usual definition that appears in Mitchell's book and that this is just That is just that it tells you what is the modulo that is in C in the position M. It's just this. And C is just any category, any K category.
But why is it so much more complicated than the other one?
Because the action now, when you have a G grading, you can decompose this, but the definition of the grading, yes, it's more or less the same, but it's more complicated because you have products and not direct sums, so you have to deal with infinite sequences. The idea is not so different, but it's a little bit more. It's a little bit harder.
Okay, I'm just asking because every time I do something with graded things, I have to remember that products in the category of graded things are smaller than general products, because otherwise the grading is not defined. So I was just wondering if the complications here might come because when you go to the graded part, the product is too big. If you take the product in the category of graded things, it collapses, but it probably gives you the same thing. I was just curious if this is why there is some problem in handling the thing.
If you look at the paper, it's the same thing. You can. Each one of those guys has the degree D, but now you have a bigger product, and so each one of those it's a little bit more complicated. It's more complicated.
Okay.
Perhaps because what you said.
Okay.
It's more complicated, but it can be done. Can be done, and you also decompose this. You decompose this complex. I didn't say what is the differential, but the differential is the usual one with the Hochschild cohomology. Now you have a different an infinite product, and you can if the category C is graded, you can decompose those along a little bit more complicated, but you can do.
¿Más preguntas?
Sí,
Dale.
I had a question about that also, but I think that it's a much more naive question. I was thinking of it as a home in some sense, like we do with usual Hochschild homology. Could that be helpful or just hide the complication?
Thinking.
Yes, I was thinking about
homology. The usual Hochschild homology, we take rings, and rings are objects with rings are category to one object. Then the product here. I didn't tell you. This is my notation. This is really home.
Yes.
Is that it's very usual. You all the time when there is a home, I don't. Oh my God! You are completely right. I mean, I did a mistake here. This is home.
No, it was.
I don't know.
I was saying that it can be like a big home in some category because the direct sum.
Only to say, if only 1 second. So if you have a ring is you can think in a category of one object. Then this product doesn't appear because here is you just have one the same guy. You have C. Now here, sorry, here is a tensor product. What you are going to have here is a tensor product of the ring all the time, and you get the Hochschild, the usual Hochschild complex for homology, for cohomology. This guy here is the this guy is by, I don't know if I put the definition here. I don't put, but this guy here is the product of C. No, I think I put in one place. Is the product of CX1X. No, I didn't. I put in the beginning. This notation here means CX1. This guy here is xn minus xn minus 1. No, xn plus 1. No, I think, yes. C, then so on, then here x n minus 1, no, xn, and here you put tensor product.
Yes, I think I understood that. But it can be looked as a home from C tensor C n times or n plus 1 times, where the tensor is over the
K.
No, over the identities, like the in the way.
Now, when you take a C, if you have a ring, this is going to be A tensor A over K.
Of course, if you have a ring, but if you have a
Category.
A ring made from a quiver, you can do it by tensoring over the K0,
over the
Q0.
This can be, this is done, you can reduce the, because when you have the usual Hochschild cohomology presentation, you can reduce this taking tensor product instead over K, you take over KQ0, let's say.
I mean, it's just a different way of saying the same. I was thinking about if it would be helpful of thinking, because when you're thinking at home, maybe there's, I don't know, you can think about projective resolutions in some way, or.
Okay, you are this is probably how you say usually very big, and certainly it can be modified, but with all this generality, I don't know how to do it. You're taking this tensor product over what? I know they are the same, so you want to take it over the endomorphism ring, perhaps, but then you have to change it. I think it gets more messy. You could take, instead of taking O times over K, you take the tensor product under the radical of the, no, under the.
I see under the category, the discrete category generated by all the identities.
Yes, perhaps yes, but this can be very big. Okay, perhaps, I don't know. I think this is can be done by our results are more theoretical than practical in general, and I don't see the way you do it, what you get. I mean, if it pays off to really do it changing, I don't see. Perhaps in some cases, but I don't see that. This would be smaller, yes, but you still have this big prod on and this is what makes it hard.
Yes, of course.
But yes, you can make it like when you have a quiver, you can take over KQ0. I see. You see. No. I think what we are doing here is taking that, because we are not taking over K, the tensor. The tensor is over K, but the the morphism goes, when you take the this is exactly the complexity you are thinking, because we take x1, x2, and the other one we require that it has to be the same. You see here, what is this? This is cx1, x1, and then here at the end I have something that ends at x2, and the next one has to start with x2. So this complex is the complex that you are thinking, is over k, is over the identities. I mean, the identities, the local identities, automatically, the way it's defined here. You see or not?
Yes, I see.
Yeah, because it's like we require here, does home, first I have to take C of the vertex 1 to the vertex 2, and the next one has to go to the vertex 2 to the other vertex. So we are not taking the whole A. We are not taking the whole ring. This is what you are saying already. The tensor, it seems over K, but it's over K, but the way we require the elements they are in the right way, that over K over E doesn't change anything.
Yes, I was thinking that maybe that I don't know if that approach would be helpful, or just hide all this.
No, but in my opinion, is that we are doing that approach. This is already done the way you think.
Yes, yeah.
This is already the way you think, because you see the image here is cx1xn, and here is cx1x2 tensor cx2 c x2 on the right, x3 on the left, tensor c x3 on the right, x4 on the left. So the guys already are coherent. So you're already taking, like, the tensor over E doesn't change anything. I think my opinion is that if you do general theory with general complex, probably you cannot make it easier than that. If you are in particular case of a quiver, then if you have a particular algebra, then you can take other presentation. This presentation is the presentation of Hochschild somehow. Is always very big. It could be smaller, but
Okay.
Okay.
Thanks.
So